In this video, we're going to introduce ourselves to the idea of photoelectron spectroscopy. It's a way of analyzing the electron configuration of a sample of a certain type of atom. And so what you'll often see, and you might see something like this on an exam, is a photoelectron spectrum that looks something like this. And so the first question is, well, what's even going on? How is this generated? Well, I'm not going to go into the details, but the big picture is the analysis will be done by taking a stream of that atom. And so that atom, there's an atom stream going in one direction, and then the other direction, let me label this, so that's the atoms that we're trying to analyze. And then the other direction, you send high energy photons that are going to bombard those atoms. Photons. Now, these photons are high enough energy, in fact, they're typically X-ray photons, so that when they collide, the photons are high enough energy to overcome the binding energy of even the core electrons. And as those electrons get knocked out, they move away and they enter into a magnetic field that will deflect those electrons and then make them hit a detector. And so you can imagine the electrons that are closer to the nucleus, those have the highest binding energy. And so more of that energy from the photon is going to be used to knock it off, so less of it is going to be there for the kinetic energy. So those closer electrons aren't going to get as far. And the outer electrons, those have the lowest electron binding energy. They're the easiest to knock off, and so you have more of the photon's energy is going to be transferred into kinetic energy. And so they're going to get further away, and they're going to hit the detector at a further point. And so one way to view the photoelectron spectrum is it gives you a sense of roughly how many electrons have various binding energies. And you can see that the binding energy increases as we go to the left. Now, the reason why this makes sense, the binding energy is inversely proportional to how much kinetic energy these electrons have as they actually get knocked off. And so this spike on our spectrum at the extreme left, these are the innermost electrons. And then these would be electrons further out with the next lower binding energy, and then lower binding energy after that. And so we can analyze this to actually come up with the electron configuration of this mystery element right over here. What do you think that would be? Pause this video and try to think about that. Well, as I mentioned, this spike right over here would correspond to detecting the innermost electrons. And so the innermost electrons are the 1s electrons. And we know that those aren't the only electrons because there's electrons that have lower binding energies. And so we know that we would have filled up that innermost shell. And so we know that they have two 1s electrons. And then we can then think that this next spike, that's going to be the 2s electrons. And we have more electrons than that, so we must have filled up the 2s subshell. And then this next spike, this looks like 2p. And the reason why this really makes a lot of sense is, notice the detector is detecting more electrons there. And we also have more electrons. And so that must have been filled. And that makes sense. And actually, the way this was constructed, it's not always going to be this perfect. But you can see you have roughly 3 times as many 2p electrons as 2s electrons, which makes sense. The 2p subshell can fit 6 electrons. 2s subshell fits 2. So this next spike is going to be the next highest energy shell, which is going to have a lower binding energy. It's easier to knock those electrons off. And so this looks like it's going to be the 3s2. And then this next spike, this looks like 3p6. And then that one gets completely filled. And we have one more spike after that. And that spike seems to get roughly the same number of electrons as all of the other s subshells. And we know from the Aufbau principle that the next we would fill is 4s. And it looks like there's 2 electrons there because this spike is about the same as the other filled s subshells. And so just like that, we're able to use the photoelectron spectrum to come up with the electron configuration of this mystery element. Its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And what element has this electron configuration? Well, we've worked on it in other videos, but I can get my periodic table of elements out. And we can see, let's see, 1s2 gets us to helium. Then you have 2s2, 2p6 gets us to neon. 3s2, 3p6 gets us to argon. And then 4s2 gets us to calcium. So our mystery element is calcium. And if someone were to ask about valence electrons, that would be this outermost spike right over here. The spike of electrons with the lowest binding energy. They have the lowest binding energy because they're the furthest out there. They are the easiest to knock off. And because they're the easiest to knock off, more of that photon energy is left over after overcoming the binding energy that gets converted into kinetic energy. So those electrons get deflected further. Now, based on what we see here, the photoelectron spectrum of calcium, what would we expect the photoelectron spectrum of potassium be? And just as a reminder, potassium has an atomic number of 19, so it has 19 protons in the nucleus, while calcium has 20 protons in the nucleus. And we're going to assume that we're talking about a neutral potassium atom, so it's going to have 19 electrons as well. Pause this video and think about how it might be different. When we think about potassium, it's going to have a very similar photoelectron spectrum as calcium, but because it only has 19 versus 20 protons, it has less positive charge in the nucleus. So it pulls a little bit less hard on our various shells. So in potassium, you're still going to have 1s2, but it's going to have a slightly lower binding energy because it's not pulled in to the nucleus as much. And I'm not drawing it perfectly. It might not be this much. Actually, it's probably more slight, probably something like this, but it's going to be a little bit to the right. Similarly, 2s2 is going to be a little bit to the right, and then 2p6 is going to be a little bit to the right. And once again, I'm not drawing it completely perfectly because I don't have the exact data here. 3s2 would be a little bit to the right. Once again, only 19 protons versus 20 for calcium, so we're pulling a little bit less inwards, so we have a lower binding energy for any given shell or subshell. And 3p6 is going to be a little bit to the right, like this. And then what is a 4s subshell going to look like? Well, it doesn't have 2 electrons in the 4s subshell. It only has 1, because it only has 19 electrons, not 20. And so it's going to be a little bit to the right. It has a lower binding energy. And it's only going to be half as high because you only have 1 electron, not 2. So it's going to look something like that. That would be the photoelectron spectrum of potassium, roughly speaking. Now, we've already talked about that your outermost shell shows where your valence electrons are. So if we're thinking about potassium, it would be right over there. Now, that also tells us, when we're thinking about the binding energy over here, so this binding energy, that tells us how much energy do we need to remove an electron. And so when you're removing that first electron, that's your first ionization energy. Once you remove that first electron, because of all of the interactions between the electrons, your photoelectron spectrum would change. So you can't think about your second or third ionization energies, but your first ionization energy, you just have to think about it's the binding energy of your outermost electrons.